Hi all, my name is Zoe Zwecker and I'm a fourth year environmental science major at Colorado College. I just want to again take a second to welcome everyone to the MEER ReflEction Project Symposium. I just want to give a quick project introduction and also a few housekeeping reminders. If you guys have questions during any of the presentations, please send them in the chat during the presentations. That way we can get back to you either when we're done presenting or right back to you at some point. Please keep your video on if possible. And we encourage you to stay and listen to all of our hard work. Thank you again for taking the time to come and listen to our research. It means a lot to have you guys here and listen to your support and feedback. So this is our mission and vision statement. Our broad mission is to provide and allow a sustainable future for humanity and the natural world. We aim to have the manufacturing capability to implement MEERs by 2030. If you want to read more about our mission and vision, you can do that on the MEER ReflEction website. So just a quick symposium schedule. This presentation is about our project motivations, climate predicaments. Then we'll move on to a conceptual framework for the MEER ReflEction project. And then we will introduce the teams and each team will give individual presentations.
Hi everyone, my name is Ellie. I'm a third year student at the University of California, San Diego, and I'm a representative from the ecological modeling team. I'll be going over a few diagrams about why we at MEER Reflections consider thermal extremes or rising temperatures to be the most urgent and devastating effect to humans. A relevant note is that August 2020 was the second warmest August on record, and the Northern Hemisphere had its hottest summer this year in 2020. Now to the diagram. First, I want to make note of the left y-axis, which is threat to humans, which increases with the arrow. And to the right y-axis, do you mind clicking? Which is visibility, which decreases with decreasing threat magnitude. So first we have sea level rise, whose effects will likely grow more devastating with increasing temperature. And next slide, And then next we have ocean acidification, whose negative effects will also grow with increased warming. And also we have pollution, which is also currently occurring and can cause significant health effects, but it will most likely not cause all of the ecosystems to collapse. And finally, we have thermal extremes. I really want to highlight this point. With thermal extremes, we'll have severe weather change, including that of drought, which could cause our food sources to collapse. And we might have temperatures that exceed our human physiology and cause us to die. Additionally, thermal extremes are so interrelated to other climate threats, such as ocean acidification and sea level rise, which we already mentioned. This is why at Project MEER Reflections, we aim to stop the problem at its source and tackle limiting thermal extremes. Awesome, and next slide, please. So the next slide I would like to talk about also relates to thermal extremes in the manner of thermal performance curves. For most organisms, examples being animals, plants, and viruses and bacteria, if you don't mind clicking to the next two. There are thermal limits where an organism can no longer survive or function once it reaches a certain temperature. And this is a sharp drop in an organism's productivity as the temperature increases. And this contributes to a loss of ecosystem function and to Earth's further energy imbalance. And thank you.
Hello, I'm Sebastian. I'm a junior mechanical engineer from Cornell University. I'm here to show you this graph, which shows the natural versus non-natural slopes of temperature and carbon dioxide increase and its fluctuations over time. As you can see, since the inception of fossil fuel energy, we have changed the slope of carbon dioxide and temperature in a drastic manner. The amount that CO2 has grown in the last 100 years is about the same that it fluctuated in the 10,000 years before that. As well, the amount the temperature has changed in the last 100 years is the same as if it had changed 1,000 years before that. So our natural system has had limited adaptation to these massive changes in CO2 and heat. Thus, we are experiencing those changes in various ways, with increasing heat in urban areas leading to rising health risks and the increased death rates of sharks, corals, and other biotic species. This is another way to produce the famous hockey stick graph from CO2 increase as well.
Hi, my name is Rashida Roy. I'm a senior at Emory University studying environmental science and chemistry. So in constructing the all-encompassing framework of this project, it was important to start with assessing our planet's materials that we have available for our use. So to start, we have the sun as the source for thermal energy. We have sand to enable the glass infrastructures. We have the oceans, which cover a vast majority of Earth and can aid in scalability of the project. We have the manpower and initiative to rally behind this goal and make the project grow. The sky symbolizes the endemic natural processes that we can use to our advantage in designing this structure, and the smoke and pollution represents the various waste sources that we can both resolve and use as a further opportunity to close our cycle.
Hi, everyone. Welcome to the first MEER Reflection Symposium again. My name is Jagger Alexander. I graduated this May from Vanderbilt University with a bachelor's in math, and I'm a first-year master's student in climate and health at the University of Miami, Florida, and I'm representing the temperature and energy modeling team. I'm passionate about finding the most practical and effective solutions to the climate crisis. And so working with Project MEER Reflection has been a wonderful opportunity for me. And I'm going to start by discussing our approach to thinking about this huge climate crisis that we're facing. So we've tried to handle each individual piece of the climate crisis by looking at it from the bottom up and the top down. So first, we're starting with the individual components and using physical relationships to understand the whole. Here's a way in which we could categorize any parts in a system into three groups: matter, like solids and liquids and gases, etc. Energy, like light, heat, kinetic energy, and various potential energy sources; and information, which encompasses physical laws and components of human systems like technology, values, and policy. So let's start by looking at the simple system of a funnel. We have a source rate of incoming water, a node, which represents the amount of water in the funnel at a given time, and a sink rate of water leaving the funnel. Here are three scenarios for the funnel. One with an equally low source and sink rate, which is the only one of these three funnels to reach equilibrium and have a constant amount of water in the funnel. One with a low sink rate and a high source rate, which overflows, and one with a low source rate and a high sink rate, which remains empty. So we could think of human society using this node diagram, with resources being consumed and regenerated at different rates. We could define sustainability as the case in which the source rate is equal to the sink rate for each individual resource. This is the only case in which the quantity of each resource will remain stable indefinitely. And this is our working definition of sustainability. So any material flux also has to be accompanied and powered by energy flux. So it makes sense to think about energy flow rates in this diagram as well, which will be denoted by red arrows. So at Project MEER Reflection, we're using this as our working definition of sustainability. We recognize that this leaves it vague as to what the ideal society may look like. It may be one with high resource and energy production to sustain a large human enterprise, like in our current society, where 96% of a mammalian biomass is either kept in humans or domesticated livestock. Or it may be one where resource and energy consumption is left more limited. But this value judgment is beyond the scope of our work. So here's a generalized picture of a node diagram with various sources and sinks whose combinations are controlled by information. So physical laws, technology, and human values. And we'll use this conceptual model to understand each of the pieces of the climate crisis that our various groups are looking at. So let's try and apply this simple framework to understand the fundamentals of the climate system. We have shortwave radiation incoming from the sun and long-wave radiation emitted by the Earth. If we add in the effect of greenhouse gases, we can see some of the heat is trapped in. Don't worry about the individual terms, but they represent heat trapped by greenhouse gases, or the greenhouse effect, which is the main contributor to present global warming. And the tau function represents greenhouse gas reflection back down to the atmosphere of infrared light, and sigma represents the Boltzmann constant. So then we could quantify Earth's energy balance by subtracting the sink rate from the source rate. And we obtain this differential equation here, which shows that Earth's energy balance in this model depends on incoming shortwave radiation, the number of greenhouse gas particles, and their relative absorption. So if we approximated that differential equation to a linear form for relatively small variations in temperature, we could get a solution. But I just want to focus in on one term so that we can start to think about some hypothetical scenarios. So we can see from this equation that from the linear approximation of that differential equation, that temperature is proportional to and decays with the exponential, a negative exponential decay curve proportional to 1 over the lifetime of a gas or aerosol in the atmosphere. So here are 3 different substances that affect our atmosphere. We have carbon dioxide, methane, and aerosols. Carbon dioxide has an atmospheric lifetime on the order of centuries. Methane has an atmospheric lifetime on the order of decades, and aerosols have an atmospheric lifetime on the order of days to weeks. So we can see here, if all emissions stopped today, aerosol concentration would drop to its baseline very quickly on the order of weeks. Methane would take significantly longer on the order of decades, and carbon dioxide would take even longer than that on the order of centuries. So we can also see, if you can go back, please, we can also see what the radiative forcing curves would look like. Anthropogenic aerosols are the only ones of these that cause a net cooling effect. So we would have a warming effect that would be realized very quickly from stopping emissions. For methane, we would have a cooling effect that we would realize over the order of decades, and carbon dioxide, we would have a cooling effect that would take effect on the order of centuries. But on the short scale, we are going to have a net warming effect that is going to continue on the order of 50 to 200 or 200 years before we actually start to cool our climate. So here's some figures that further illustrate the point that if we stopped emissions today, we would experience a warming of about 1 degree Celsius that has been masked by aerosols, as well as continued warming from greenhouse gases for hundreds of years before we reach an equilibrium temperature. So this figure has data from 2005, and it was estimates then of what our committed warming would be as a society. So it was estimated in 2005 at around 2.5 degrees by the IPCC. Today, this curve has shifted significantly to the right after 15 years of additional fossil fuel burning. So we would expect significantly more warming, though I won't make claims to an exact number. One solution that is often proposed to remediate the climate crisis is planting trees. A 2014 study at ETH Zurich aimed to study the net radiative forcing effects of turning land that was used for farming into forest land. Their finding was that there was a local change in net radiative forcing of -24, so slightly cooling effect to +2 watts per meter squared, which is a very, very small warming effect. So what do these numbers actually mean? Also, I want to emphasize that the reason this effect is smaller than you might expect is because we have the carbon dioxide uptake, but we also have to subtract off the albedo forcing, which is going to be positive when we change the land use in these areas. So these numbers, if we take the maximum number that they found of -24 watts per meter squared, we can calculate that it would take reforestation of about over 50% of Earth's land surface area to offset anthropogenic greenhouse gas radiative forcing. And if we assume an average of half of what they found, more in the middle, -12 watts per meter squared, it would take over 100% of Earth's land surface area to offset anthropogenic greenhouse gas radiative forcing, which would take some creative solutions to say the least. We should note that forests already cover 30% of Earth, and glacial ice covers another 10%. Oh, sorry. These are only Earth's land surface values. This is also only in the case that we could magically turn land into mature forest immediately. So we can see that this may not be a practical solution to solving the climate crisis immediately. So these dilemmas lead us back to our main mission at Project MEER ReflEction. We're aiming to provide technology and realistic solutions to close the loops in our material consumption and minimize our energy and resource flux without having to sacrifice the scale of the human enterprise. From our bottom-up and top-down frameworks, we believe that the most effective way to stabilize the temperature is to reduce the net incoming shortwave radiation that is converted to heat using mirror arrays. The other groups in our project will discuss our rationale and justification for this proposal. So here are some references, and we can take questions now.